Alright, so in today's tutorial, we're looking at some example of simulation in R, and we'll be using the arrays data set. The arrays flower data set is a multivariate data set introduced by the British statistician and biologist Ronald Fisher in his 1936 paper. The British statistician and biologist claims the sepal length of the species are determined by the sepal width of the species. So there's a claim that the researcher is trying to make. What do we seek to achieve here? We want to fit a simple linear regression model and record the slope, intercept, and p-value of the model using R. So let's get into R. So here we are in R Studio. First of all, I have to look at the structure of the arrays data set. So I'm going to use str arrays, right? So let's run this. I'm going to run this. So we have 150 observations of 5 variables, but the claim that is being made by the researcher is saying that the sepal length is being determined by the sepal width. So once we know the sepal width, we can actually predict how the length is going to look like. So we have to define our variables, right? So we are going to assign the sepal. We are going to assign the sepal width to x. That's our independent variable. Then we will assign the sepal length to y. That's going to be our dependent variable. So I think we are good to go. And our objective is to fit a simple linear regression model and record the intercept, slope, and p-value. So let's first of all look at how the regression model is going to look like. Let's say we have LM, linear regression model of y total x, right? So let me define it. Linear regression model, right? So when there's regression model fit, so this the linear regression model dot fit. So you can look at a summary of our linear regression model fit. So let's run, but we are interested in the coefficient, right? So let's be specific. We are interested in the coefficient. So let's run this too. Oh, spell a mistake, right? So let's run this, run everything. Okay, so that's basically the information given to us. So the estimate for the intercept is given to be approximately 6 or 7, and the estimate for the slope is approximately minus 0.22, right? And the p-value for the overall model is the same as the p-value for the slope estimate, right? This is the p-value for the regression. If you have to look at the ANOVA of our model, you realize that the p-value is the same as the slope estimate of the p-value. They are actually the same. So if you look at this p-value for the ANOVA as compared to the slope estimate, the p-value for it, they are basically the same, right? So basically we want to get this estimate, the intercept, get the slope estimate and the p-value. So how do we do that using R? We have to create our own function to be able to get this estimate. So we are going to write a pseudocode for the regression for fitting, or let's say for intercept, slope, and p-value. Right, so that's basically what we need. So I'm gonna call this linear regression model dot f. That's the name of the function that I want to create. I just need two parameters. The a stands for the independent variable, and my b stands for the dependent variable. Right, so I think we are good to go. So can look at a linear regression model fit, which is going to be lm b total a. Right, so once we have this, we can look at a summary. I'm using SS for summary of my linear regression model fit. Right, so once I have this, I can then get, because the coefficient that we have is in the form of what? A matrix. You have 2 rows and 4 columns, 1 2 3 4. So we have to design our function in such a way that we can get the estimate that we are interested in. So we need an intercept estimate. So from the summary, I need a coefficient, and I need the intercept can be found in row 1, column 1. So 1 1. So intercept estimate. I'm gonna copy this and paste. So I need a slope estimate now. So SLP for slope estimate. So slope can be found in row 2, column 1. So I'm gonna use 2 1. Right, then I need a p-value estimate. So p-val can be found in row 2, column 4. Right, row 2, column 4 give me the p-value estimate. So this should be slope estimate. This should be p-value estimate. Right, so once we have this, we can return our results. So we need the intercept. So I'm assigning the intercept estimate to intercept, giving a name to it, and then slope to slope estimate, then the p-value. I want to assign the p-value estimate p-val to that. So we should be good to go. So once we run this function, it should give us only the intercept, slope, and the p-value. That's what the question 1 seeks to address. So question 1 seeks to address. Right, pseudocode for intercept. So let's run this. Oh, Control Z. Control Z. So let's run this function. I'm gonna run this. Alright, so let's call our function linear regression model function. I just need my x That's the independent variable, and y, which is my dependent variable, which I've already specified, right? So let's run this and see the results. I'm gonna run this, right? So that's it. It gives us the intercept, slope, and p-value, right? So now we are good to go with question 1. Let's look at the next question. What are we supposed to do? We are supposed to randomly sample 15, 30, 50, and 100 samples from the iris dataset and perform 1,000 and 5,000 simulations for each case and record the slope, intercept, and the p-value of the model. How do we do this? Using the R software. So back to R, question 2. We want to record the simulation. So let's say the code for simulation, right? So basically we can do this quite easier if we write our own function. Then I think it makes things easier. So we are going to write a function to help us to get the simulation done for the 1,000 and 5,000 simulations, right? So I'm going to create a function, call the function sim.f function. So I'll need only the sample size and number of applications. So n equal to sample size, and my big N is equal to the replications, right? So I think we are good to go. So we have to create a container so that it can store the intercept and slope and the p-value, right, for each replication. So I'm going to name it estimated values, right? Estimated val equal to matrix. I need an A. Number of rows should be equal to the replications. Number of columns should be equal to 3, because we need only 3 estimates, 1 for intercept, 1 for slope, 1 for p-value, right? You can basically look at how it works. Matrix, let's say an A missing observation, right? Then n row equal to, let's say 5 if you are doing, let's say 5 applications. Then n column, number of columns should be equal to, let's say 3. Let's look at how it looks like. So this is basically what we're trying to do. So for each run or each experiment or replicates, we are going to get 3 estimates, 1 for intercept, 1 for slope, and 1 for p-value. So in this first column is going to always store the intercept. In this second column is always going to store the slope, and in this third column is always going to store the p-value. So that's basically what we have created for this. So let me take this off. So so this is an empty matrix to store intercept, slope, and p-value estimates, right? So I think let's move on. So I think once we have this, we can basically use the for loop to compute our simulation. So for index I in 1 to n, for I in 1 to n, what do we seek to do? For I in 1 to n, we have to sample with replacement, because for each replication it's going to store the intercept, slope, and p-value and perform another experiment from the same sample. So this sampling has to be done with replacement. So sample with replacement. So sample 1 to n, size n, then replace should be true, right? Then so this is basically sample with replacement. Then you have to sample from the sepal dot with replacement. So it's going to sample from the iris data. I can use iris sepal dot width, and let's say use sample with replacement. But since I've already specified x, so I can also use x sample with replacement. I've already assigned the sepal dot width to x, so I can actually use this instead of using this. Whichever method you use should get you accurate or the actual result that you are looking for. So let's move on. Let me make this x1 and y1 to differentiate it from the first one that you have already assigned. Then the iris data sepal dot length, that's my independent variable, sample with replacement, right? So sample with replacement from the sepal width, sample with replacement from sepal length, right? So once we are done with this, we can look at a regression. So the regression model fit. So linear regression model, I need to use let's say I've already created a function, right? So I can use that function, linear regression model dot function. X1, that's my independent, y1, that's my dependent variable. Then actually this will always give me 3 results, a vector of 3 results, intercept, slope, and p-value, right? So from here we can store the estimates for each replication. So we want the first index to be stored as the intercept. So linear regression model, we want the first index to be stored in this container that we have created. In this container, the first for each replication, the first index should be stored in here, right? So store intercept for each run, right, or replication. Then we do the same for the slope. So I'm going to change this to 2, right? So store slope for each one, then copy paste for the third estimate, which is the p-value. So store in this column, that's I for each replication, store in the third column p-value, right? The p-value is the third index for my model, right? So I think we are good to go. You have to ensure that this is a data frame. So let me give a column names for my, because this column doesn't have a name. So column names of the estimated values. I want it to be such that the first column is giving the name intercept. Right, the second column is giving the name slope, and the third column is giving the name p-value. Right, and I also have to ensure that it displays my results as a data frame. So I'm going to put it in a data frame as data frame s not bars. So display results as data frame. I think we should be good to go. So let's run this and look at the, let's highlight and run to see the result that we are going to get. So I'm going to run this. Right, so we're going to start with, we are supposed to sample 15, 30 and 50, 100 from the array data set and perform 1000, 5000 simulation for each case and record the slope, intercept and p-value. So let's name this 1000 simulation for a given n. Right, so I'm going to name the first one S1, that's simulation 1. So I just need the head. Let me call the function sim.f. Right, I need n15, then the replication 1000. So this is basically 1000 simulation for n equal to 15, for sample size of 15. Right, then let me copy this and paste. Right, I can do the same for when n is 30. So I'm going to change this to 30. Then I can make this S2. Then do the same for when n is 50. S3 when n is 50. Right, then the last when n is 100. Right, so S4 simulation 4 when the sample size is 100. How would the results look like? So I'm going to run the first one. Control enter to run. So it's running. See the run indication. Then we can look at the head to see the first 6 observation for the simulation. So I'm going to use head to get me the first 6 observations for the simulation. So when I run this, so that's basically what you are getting. Right, so you can see that this is not getting closer to the parameters that we specified. Let's see for sim2, simulation 2 for 1000 replications. Head S2. I'm gonna run this to see the results. It's still running. Head S3, head S4. Right, so I think it's still running. Once it's done, we will see the output. Okay, so it's done. So not pretty well it's not getting closer to the parameters that we specified, or yep, it's not closer. So let's look for n50 for 50 sample size. How would it look like? I'm gonna run everything. So somehow, but not closer. Let's look at the last sample size of 100. How would the estimate behave? So I'm gonna run this. How? So you see, for a sample size of 100 is performing better as compared to when a sample size is below 100, right? You can see that it's now getting closer to the estimate, the parameters that we actually specified, right? You can see from the result that we initially had from our estimate. Let me run this. If you look at the result that we had, it was approximately, let's say 6.5, approximately minus 0.2, 0.15, right? But you can see that now when the sample size was increased to 100, you can see that it was actually performing well. You can see that the estimates are now getting closer to the estimated values that we run for just for one experiment, right? So this is how the simulation is actually behaving for a given sample size. Now we can copy this and just change some values to run for the 5,000 replications. So what if we have 5,000 replications? How will the estimate behave? So I'm gonna change this to 5,000. So n now is 5,000, and now is 5,000, 5,000, 5,000. I'm gonna change this to s_1, s_1 to differentiate it from the 1,000 simulation. _2, _2. I'm gonna change this to _3, _3. Then this _4, _4. Right. So let's run this for the first one. I'm gonna change this to 5,000, this to 5,000, this to 5,000, this to 5,000. So we can run this now, right? So basically it's running. I'm gonna skip some, right? So you can just be running it to compare the results and see which one is performing. So you can see the results, the intercepts are not close to the specification from the first experiment, right? But as the sample size increases, you can see that it will be getting closer to the first specification, right? So I'm going to run this too. I'm going to run this. It's still running. Once it's done, this won't show anymore. So I have to wait for it to finish before I run the next simulation. So that's for the second. Let's look at the third. I'm running for the third. Then I'm gonna run for the last one, fourth one. Once it's done, I'm gonna run. Okay, so let's look at the last one. So we can see that always when the sample size increases as compared to when the sample size is very small, you can see that the estimates are not close to the specification of the estimated parameters that we are trying to achieve. But once the sample size increases by the central limit theorem, you can see that the shape or the estimates actually tends to get closer to the specification of the parameters that we have. So I think we are good to go. Let's look at the next question. Let's look at the next question. We want to find the mean of the slope and intercept in the second step, or the second question. How do you find the mean of the slope and intercept? So let's go back to R. So I'm going to modify this. So 1000 simulation for 1000 simulation for a given n, and estimates and the mean estimates, right? So I'm going to adjust this. So for the first simulation, I'll have to find the mean of the slope and intercept. So I'm going to use the apply function to help me get that. So the array is for the simulation. The simulation is actually in the form of what? Data frame, right? So we are good to go. S1, but we just need the first two columns. We don't need this. We just need a mean for this and that. So I have to specify it 1 to 2. So I just need the first two columns, and the margin is 2. I'm looking at the estimate for the column index, right? Then the function, we are going to use the mean. I want to find the mean for these two estimates, intercept and slope. So this is a mean estimate for for intercept and slope, right? So I'm going to copy this and do same for the second replication or the second simulation. So S2, I'm going to change this to S2, right? I'm going to copy, paste. So S3, copy, paste. S4. Right. So let's run the first. Let's run this. We have done, so we can just run this, right? So I'm gonna run. So you can see the mean for the estimates is actually not getting closer to the estimate, right? The actual estimate that you're supposed to get for the given sample size. You can see that when the sample size is small, we are not able to get closer to the estimated parameter. Let's look at the second. When the sample size is 30, is now gradually increasing, but not closer to the estimated parameter that we are trying to look at. Here we are treating the first specification of the intercept and slope as population. That's why I keep making reference to estimated parameter, right? So we can see this is not closer. So that's how we find the mean of the slope and intercepts. I'm gonna run this. Once the cursor is on the line, I can run, right? So not closer. Let's look at the last one. I can run. See, now it's getting closer to the specification that we initially had. It was around 6. The intercept was around 6.5, and the slope was around minus 0.22 here. So you can see that once the sample size is large, our estimate keeps getting closer to the estimated parameter, right? Now let's do the same for 5000 simulations. So I'm gonna paste So let's change this, and 5,000 simulation for a given sample size and mean estimates. Right, so I'm doing basically question 2 and 3 on the same place, right? So I'm gonna change this to _1, right? I'm gonna paste and change this to _2, paste and change this to _3. Then I'm gonna paste and change this to _4, right? So let's run for each. So I'm gonna run for this, right? So that's also the mean. Consider slope and intercept. You can do the same for the second. For 5,000 simulation, when the sample size is 30, what's going to be the mean and the mean of the slope and intercept? So run. That's the result shown, right? Do the same for the third. Run. Right. Do the same for 4. So you can see that always when the sample size is a little bit higher or is sufficiently large, we see that the estimate keep getting closer to the estimated parameter, right? So I think we are done with the question 3. The last but not the least, we want to draw a histogram for the intercept and slope for each simulation such that the plot of the intercept and slope for each simulation is on the same plane. So how do we do this? So let's come back to our studio. So I want to histogram. This is basically the 4th question, right? So histogram plot, right? Or let's say, because I'm basically going to use a function to get the work done easier. So I'm going to write a pseudocode for plotting histogram, right? This should be good. So, but I first of all need to load some package. If you have not installed, you can install these packages. Install .packages. We need to install these 2 important packages, ggplot2, and we also need the grid extra. Right, these 2 packages are very essential to help make our graphics look nicer. Okay, so I've already installed this, so I'm going to skip and just load library ggplot2. Then I also have to load the grid extra, right? So this is basically going to help me to have the same the 2 plots on the same plane, right? So I'm going to run these 2 packages. So I'm going to create a function to plot the intercept and slope. So I'm going to call this hist f. That's the name of the function, histogram function that I want to create, right? So in this I just need the simulations. So sim is for simulations, right? And what next? So I'm gonna start with histogram for intercept estimates. So I'm gonna call this intercept plot on ggplot I need I basically need the simulation. So sim, right, and then for this particular simulation I need to get a static mapping, right? The x coordinate, I need sim, I just need to plot the first column, which is the intercept, and then also need the y coordinates. I want the y coordinate, I want the density, so let me use density, right? So let me continue. So we have to add the the geom histogram to get a histogram. I want to fill this with, let's say, blue color, right? Then my bins should be the default 30, right? It's okay. Then we can also add on xlib. So I want the label for the x, that's the x-axis. I want the label should be intercept. Then gingy title, I want to give a title for this plot, so I'm going to call it histogram of intercept estimates, right? So I think we are good to go. So that's for the first plot. Let me copy this and do same for the slope. So copy paste, right? So I'm gonna call this histogram for slope, histogram for slope estimates. So I'm gonna change this to SLP, meaning slope plot. Same, but I'm interested in the second column, which you always, for every simulation it has 3 columns. We have the intercept for the first column, second column is the slope, and the last column is the p-value. So the second column basically going to give me the slope, the density, everything works. I'm going to change the color to green, right? Green, so okay. Then the xlib should be slope, then histogram of slope estimate, right? So now we are good to go, but we have to ensure that the same, we have the plot on the same plane. So I want to plot the 2 graphs on the same plane. So I'm going to use a grid dot arrange from the grid extra package. So I'm going to have the intercept plot followed by the slope plot. And then the number of columns should be 2, right? So 1 row, 2 columns. I think we should be good to go now. So I'm going to run this function. I'm going to run this. Okay. So from this point we can then just look at the various histograms. So I'm going to start with 1000 simulation, right? Histogram plot for the 1000 simulation. So we assigned S1 to the first simulation, if you recall. So I'll just call a function hist function and just get a simulation S1, right? I'm going to repeat this 4 times. Let's define it. So histogram. Okay, since we already know this, let me just copy and paste. So S1, S2, S3, S4, right? Then I'm gonna copy this, paste, right? So histogram plot for the 5,000 simulation. Each one we need an intercept and slope for each plot. So this we used for the 5,000 simulation, we use the underscore. So underscore, 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 underscore. Right, so I'm gonna start with the first one to see how the plot will look like. Alright, so I'm gonna run this. So running out, so I think it's being displayed. Let me zoom. So it's still loading. I want us to have a clear picture of the graphics that we have just plotted. So now this looks nicer, right? So we can see that the shape for the intercept and the slope seems to follow the Gaussian distribution, right? So I think we are good to go. We can do the same for each of the simulations. I'm going to run the second one. So you can see as the sample size increases, the Gaussian distribution is becoming more apparent, right? You can see that for the estimate, and this basically following the central limit theorem, right? For the 5,000 simulation, let's also look at how the plot looks like. So you can see, which looks very nicer. Wow, so you can see for the 5,000 replications as compared to the 1,000 replication, you can see that the mound shape or the Gaussian distribution is being revealed once the replication increases, so the sample size is sufficiently large. So I think we are pretty well to go. So this is basically how to solve this problem using R.